Okay, folks, what you got? Any questions? Okay, what y'all got?
We do 3 from the 2025 exam.
3 from 2025. Final exam, right? Okay. All right, so here's what the problem says. It says, let's let P from G to H be a homomorphism. Homomorphism. I show kernel phi is normal G, and show if G is finite and phi is onto. Then rise. Okay. First things first, show the kernel of phi is normal in G. Okay, what's the first thing we got to do there? I just want you all to be careful because you need to show it's separate, right? Because to be normal, first and foremost, separate, right? So notice that for one, let me first point out that the kernel is not empty. Well, why is that? Anybody name something that's in the kernel? Can you identify something in the kernel? Well, you're not saying the identity is in the kernel, so it's not empty, right? Because the identity in any homomorphism, the identity of G has to go to the identity page, right? Since it's not empty, all I have to do now is use the subgroup criteria. So what does this mean? This means phi of X and phi of Y are both the identity of H, right? And notice that also phi of Y inverse. So phi of Y inverse, because the inverse of the identity is the identity, right? Everybody cool with it? So now let's put this together. If you look at phi of XY inverse, this is phi of X, phi of Y inverse, which is the identity of H times the identity of H. So XY inverse is in the kernel of phi. So kernel of phi is the same. Everybody okay so far? So now we're on rock solid. We know it's the same. Yes. So what's in that?
Oh, never mind. I take it back. That's stupid.
So you're good.
Yeah.
Okay. So here's what we have now. We just have the kernel phi is separate. Now we got to do the normal part, right? So So now need to show if X is in kernel phi and G is in G, then G inverse XG is in the kernel of phi. Right? And that's the part that's going to give the subject. So, everybody okay with it? Okay, so to that end, look at phi. I mean, to show that this is in the kernel, all I really have to do is show that this thing's going to barf out the identity. Well, let's see what happens. This is a homomorphism. So I can do that. Right? And what can I say about this fit in the middle here? That has to be the identity because I'm assuming that X is in the kernel. So that's the identity. So this collapses to once again using the homomorphism property. And so we come to the conclusion that so kernel free is one. Everybody okay? Okay, so we've conquered number one. Everybody clear on how that worked out for us? Okay, how about number two? So now we get to tumble a bunch of assumptions on it. Two, G is finite and phi is onto. You need to show that the order of H divides the order of G. Well, okay. One thing that I can say for sure is the order of H is also finite. Somebody tell me why? This is a finite set. And we also said that this is the map is surjective, right? So that means the cardinality of G is greater than or equal to the cardinality of H, right? Because this map is onto. Everybody okay with that? So in particular, G is finite and H is finite because the cardinality of this is greater than or equal to that. What was important there is G is finite and that the function is onto. The function wasn't onto, I wouldn't have a leg to stand on. Okay. Now, what about this division business, right? Okay, so now I know that H is finite. How do I know that the order of H divides the order of G? Any ideas on how I might do this? Or what theorem might be useful in this situation? Which one? Yeah. I mean, that would be. Here's a problem though. You're sort of right. The problem is this is a homomorphic image, right? So H is not necessarily a subgroup of G, right? Lagrange's theorem says is okay, if you've got a subgroup of G, then the order of the subgroup divides the order of the group if they're both finite, right? Yes. Yeah, I think I'm gonna go with the first one. You might be able to do that, but so let me just kind of write down the conclusion. G mod the kernel of phi is isomorphic to the image. Everybody stay with that? Now, what do we know about the image of phi? What do we know about the What do we know about phi? It's onto, right? So the image of phi should be what? Should be all of h. So the order and Raleigh now it's going to start to look like the Rogers circumstance. Since these two groups are isomorphic, then their orders have to be the same, right? And here's the Lagrange theorem part. Which is I can say this since both G and this subgroup are both finite. Right? That is, the number of left cosets, that's the size of this group, the number of left cosets of kernel phi and G is equal to the order of G divided by the order of kernel phi. Right? And this is H. Therefore, the order of G is the order of kernel phi times the order of H. And so by definition, since this is an integer, of course, we have the order of H divides. And that's the last piece. Any questions? Yes.
Why is it?
Because the kernel phi is a subgroup, right? In a subgroup, when I ask you how many elements are in the subgroup, that has to be an integer, right? Right, you can't have 3.5 elements in a subgroup, right? It has to be just some number, whatever the number of elements are in there. Other questions? So you asked, so was that okay?
Yes, sir.
Okay, other questions? Yes.
I had a question about a definition. It's from the 2020 or final exam, but it says let R be a commutative random identity in S. If R, I'm also like an example is set if R1 over S, R2 over S2 are elements of the localization of some S, what does it mean? R1 over S1 and R2 over S2.
To be equal, right? What, which, this is from definitions where?
December 2020.
December 2020. Okay. So I'll write that down for folks. Okay, so. Right, this is number K, right? So I'll write this down for the benefit of everybody. R, Peter, 1, S, R, multiply, set. And really the meat of the question here is, if R1 over S1 and R2 over S2 are in this localization that we form, what does it mean Let me try to stimulate your memory a little bit. What does it mean for two, just think of two rational numbers, right? Pretend that R1 and S1, R2 and S2 are both integers. What does it mean for two fractions to be equal? What's kind of the easiest way to tell? Well, you do the cross multiples, and if you get the same thing, right, like 1/3 is the same thing as 3/9, because 1 times 9 is 3 times 3, right? We'll do something like this. That's what it would mean normal, but actually, does anybody remember, we're gonna change this a little bit. Y'all remember that? That's technically the most general. What it means is there's an element of the multiplicative flow set S, such that S times the difference in the cross multiples is equal to 0. Right? Now, if R is an integral domain and S doesn't contain 0, then this collapses just to this. Okay. So in most of the practical cases you might look at, it's really just the cross multiples are the same, but in the most general set, right, in general localization, you actually need that extra kicker that S times that thing to 0. Any questions on that?
What does that mean?
What's that now?
What does that mean?
Well, what it means for these two fractions to be equal is if you can find some other element of S such that S times R1 S2 minus R2 S1 is equal to 0. That's what it means for these two fractions to be the same. That's,
Or like, what does that show?
there's nothing to show, it's a definition, right? So it's, that's the way we define it, right? And there's a reason we define it that way, because it turns out you actually need this in general to make this really an equivalence relation. So there's a reason that we do this that's bona fide. But as far as doing a definition, that's all you need to know. That's what the rule is. Is that cleared up? Okay. Other questions? Yes.
We do 6 on the Alexander 25.
Okay, sure. Okay. Show the equation x squared minus 3x squared. Five. So you cannot find two integers x and y that balance that equation. Can't be there. Gosh, this seems hard, doesn't it? Right? Because there's infinitely many pairs of integers to try, right? So that's, even though this test exam period is a little longer, I'm not going to go through infinitely many things in 2.5 hours. So I need a shortcut here. Any ideas? This is basically kind of a Chinese remainder theorem type problem. Some of you might think of this as reduction mod or some number. Let's suppose that such a solution exists. So basically, I balanced this equation. Now, there's many things you can do, but there's one thing you can do that might be a little bit more clever. There's a homomorphism that goes from Z to Z mod 3, right? And that homomorphism, here's how the homomorphism works. Take any integer. What does the homomorphism do? It divides by 3 and takes the remainder, right? So the homomorphism takes 1 to 1, 1 bar, say. It takes 2 to 2 bar. It takes 3 to 3 bar, which is 0 bar. It takes 4 to 1 bar, 5 to 2 bar, 6 to 3 bar. It just keeps cycling, right? What happens to this equation when we subject it to this homomorphism? Well, this becomes p of x squared. What does this become? What does the homomorphism do to 3? It goes to 0 part, doesn't it? So this is basically, this goes to 0, right? Because it goes to the 0 element of, so this is like minus 0 bar. What does it do to 9? Same thing. And this goes to 5 bar, right? Which is the same thing as 2. So if this solution exists, then it gives rise to this solution mod 3. If I agree with that, in Z3. Now, let me just make a simple table here. Well, if p of x was 0 bar, p of x squared would be 0 bar. The 0 bar squared is 0 bar. P of x is 1 bar, p of x squared is 1 bar. And what is 2 bar squared to? Mod 3. Squares to 4 bar, which is also. Do you ever get 2 bar in this column? This has no solution. Right? Because you can't square anything in Z mod 3 to 2. This is a contradiction that we wanted. So, no solution x, y, and the integers to previous equation. This is one of the coolest applications, really, of the Chinese remainder theorem or homomorphisms, whatever you want, because it takes this equation that has potentially implementing things you can try, boom, you reduce it down to this much more compact equation, and there's only 3 elements of Z mod 3. We tested and we found that none of them work. Therefore, there can't be an original solution. Now, you might complain at me and say, what if there was a solution there? Well, that's a little bit more delicate because just because there's a solution there doesn't mean that there had to have been one in the first place. Right? And that's more delicate analysis. But it certainly does help to eliminate things, right? Okay, questions on that? Yes.
It's gonna be dumb questions. Sorry in advance. The mod 3, did you get that right? So it's like thought ahead and want the 3 and the 9 to consider more.
That's exactly right. That's exactly right. And that's a good observation. There's nothing special about mod 3. I could have gone mod 5, mod 7, mod 10, mod 8, 6, 7, 5, 3, or 9, whatever I wanted. Why did I choose 3? Because it made this graph go away, right? This is where all my variables, see, I've got 2 variables here. The 3 kills these things, and now I'm only dealing with 1 variable, right? Makes it easy. So yes, you could do other things. I think this is probably the best way to go for this particular. Other questions? Yes.
Could you number 9 from the spring 2021 example?
Spring 2020. Those are computer room. Do they? For this one, it might help to remember this. Remember this from the earlier, the question about the definition, which now I'm quite happy that you asked. So here's the problem at hand. Suppose R is a computed ring with 1, S is multiplicable closed set. So suppose that you have a nilpotent element S. That's what the question says. Any ideas? By the way, what does it mean for S to be nilpotent?
That there's a natural number n such that SCN will equal 0.
Okay, good. So let's do a little technical here. Now, what else do we know? We know that S, capital S, is a multiplicable closed set, and little s is an element in it. So little s to the n is 0, right? What does that mean about 0?
It's in S.
It's in the multiplicable closed set. Everybody cool with that? So now can you tell me how many elements are in this?
1.
set. Only one of them. Why? Well. Let R1 of S1 and R2 of S2 be any two elements. Of I think you could all agree with me. Everybody agree with that? If I multiply zero by the difference in the cross multiples, I get zero. And this is a legal move because this is in S by our little reduction over there, right? If there exists S and S such that equals zero, well, all you have to do is take S to be zero. This implies all are correct. So there's only one element in this localization, namely the zero element. They're all the same as zero over one. Right? Everything's the same. That is one of the reasons why in a lot of the theorems that I gave you earlier, I said, let S be a multiplicative set that doesn't contain zero. Because what happens if it contains zero is you get a very boring ring that only has the zero element in it. Not too exciting. Questions on it? Okay, other questions? Yes.
Can you refresh my memory on what we would do if zero was not an S?
Oh. The answer to this question, zero is not an S, is I've got no idea, right? I mean, it depends very heavily on what the ring is and what the set is. And in fact, in most examples, it's probably an infinite number of elements in there. Right? But yeah, all bets are off. In fact, the only way that this problem makes sense is if I actually specifically gave you a finite ring and a finite set S, the zero wasn't in. And then you could probably go through and count. But I'll be honest, you'd have to go through and check which equivalence classes are the same, different. That won't be great, man. So, you know, that's just a nightmare. Okay, other questions? Yes,
Could you do number 5 on our exam 2 from this semester?
exam 2, yes. This is the last problem last week, 5, right? So this was the famous last problem on exam 2 this semester. So R is arranged an element A and R with the property of A squared. A is called idempotent. Okay, so if it squares to itself, it's idempotent. Actually, in more general ring theory, idempotents actually are quite important. So in this problem, we have R. A, we can bring what? And then C, R to T is a homomorphic. Well, like I said, this was the last problem on class test. How many of you all found this problem a little intimidating? Right? Yes, I totally get that. But just take a breath, just kind of let the words lead you, right? What does it ask in part A? Show that phi of 1R is an idempotent. Okay. First of all, phi is a function that goes from R to T. And we also know that R is a ring of identity. So 1R is an element of the ring, phi of 1R is an element of T. So at least it's probably make a little sense to me. How do you show something's idempotent? Just square it and see if you get it back. So let's do that. Let's just square this. Okay. Let it be dramatic. Not flare for the dramatic. I like this. This is what? That's what phi of 1R squared is. Now what can I do? Any ideas on the next step here? The big thing here, right, is phi is a homomorphism, right? So I can write this way. Everybody agree with that? And what happens when you square 1R? What's 1R times 1R? So look what happened. When I squared it, I got it back. So it's not. Yes.
Just said that it's a homomorphism. This or to say phi of 1R is 1 to T.
No, because I know what you're saying, because I said that that's usually the way I define things, right? But here I didn't, don't really confuse it. What I had said earlier in class is usually we take a homomorphism, we take the identity of ring to another identity, but I'm not making that assumption here. However, if that was the case, it certainly would be true, wouldn't it? Because if you take 1R to 1T, well, the identity of T is certainly idempotent as well, right? And actually, we're going to prove under these conditions, this does turn out to be the identity of T. So in part B, this part B seems like a bit of a non sequitur. It's just kind of, but it ties in later here. Part B says, show if T is an integral domain, that the only idempotents are 0 or 1. Only idempotents. Are 0 and I guess if I was really careful, I would should write 0T and 1T. Yes. Okay, well, let's do this. By the way, let me also point out T is a ring, right? And so it contains 0 for sure. And I also said that T is a commutative ring with identity. So one T exists in T, right? So T does have zero and it does have an identity. Am I good with that? Well, A be any idempotent. Then, I don't know much, but I know that A squared is equal to A. Right? Now what? I need to do this, A has to be either 0 or 1. This reminds me like kind of in high school, right? And in a certain sense, that's what I'm gonna do. Like, you know, your teacher in high school wants to solve this equation, right? Obviously, we're in a much more abstract setting, we're in high school, but we can kind of follow the same rules. Correct? And I can pull out an A. Pulling out, pulling that A out is actually, I need the fact that T has an identity. Because if there's no identity, I couldn't pull that out. Okay with that? So far, so good. Now, what are we assuming about T? It's an integral domain. And so what does that mean? We've got the product of two things being zero, that means one of them has to be zero. So since we have a domain A equals 0 or A minus 1 is right. So A equals 0 or A equals, yeah. So any idempotent has to be 0. So if you ever want to have interesting idempotents, you need something to stop in the middle of the night. Finally, show that if T is an integral domain and phi is not the zero homomorphism, then phi of 1R is equal to phi of 1T. So this is final proof. So, C, show if T is an integral domain and phi is not 0. Then phi of 1R actually has to be phi of 1. So if both are computed proofs with identity and T is an integral domain, then this is forced. Phi of 1R has to be. If it's not the 2. Okay. Any ideas on how to proceed? This really isn't so bad. What is part A give us? What do we know about phi of 1R? Part A is it has to be identical. But this is, of course, an element of T. And what are we assuming about T? It's a domain. Therefore, phi of 1R is equal to 0 or the identity of T by part B. Because that phi of 1R looks at T and it's idempotent. But T is a domain. That means that idempotent has to be either 0 or the identity. Everybody okay so far? So now we've got our list of suspects down to 2. So suppose first that phi of 1R is 0. Can somebody tell me why this can't work out well for us?
Does the identity and group homomorphisms always have to map to the other identity?
Let me be careful with what you said. For groups, yes, but that means that the 0 element of R has to map to the 0 element. Now, it is not true that the multiplicative identity of R has to go to the multiplicative identity of T. But we're saying that in these restricted conditions, it does. And that's why if you read in an algebra, it will sometimes be the case, some authors will assume that you take the identity to the identity. And some won't. You don't have to. Right? For example, if you have the 0 homomorphism, you take every integer and go to 0, that is a ring homomorphism, right? But you certainly don't take the identity to a multiple identity, right? It goes to 0. Let's suppose that you take the identity of R of 0. I claim that this means it's 0. For all R and R, phi of R is, this is a real cheap trick. This is phi of 1R times R. I think we have to agree with that. But because this is a homomorphism, this is phi of 1R times phi of R. And phi of 1R is 0 by assumption. See. In this case, phi is 0 homomorphism. Because what we proof here is if you take the multiplicative identity 0, you're forced to take everything to 0. All right? Yes.
So just saying that phi of 1R equals 0 isn't enough, like, because I thought like you could just say that's like the 0.
Well, to be the 0 homomorphism, what that means is it takes everything in R to 0. Right? Now, what we've shown is if you take 1 to 0, then you have to take everything to 0. And that's a no-no. Right? So phi of R had to be either 0 or 1. But we found out that if it's 0, it takes everything to 0. Well, then I said it's not supposed to be 0 homomorphism. Therefore, phi of 1R, no choice. That's not too bad, right? Okay. Other questions? Yes. Okay, right. Did you have any questions for you? Okay. Are you good? Euclid. Okay, do remember this. The Euclidean domain is a domain. So it's an integral domain. So it's a commutative ring with identity, and it's got no non-zero zero divisors. But it's special. There exists a function phi in the non-zero elements to the natural numbers union 0. Some of it takes none. It doesn't as long as it's a non-subset. satisfying. Number one. So for every X and Y which makes sense, that it's not zero almost R, phi of X plus X. And two, for all X, Y, and all minus zero. So if you pick any two elements, any two non-zero elements of R, you can divide Y by X, you get a remainder. There exists Q on R and R. These could possibly be zero, such that Y is equal to QX plus R. This is essentially what we've done. We've taken Y divided by X, it's got quotient Q and remainder R. And my remainder, this is the fancy part of this. R is equal to zero, or the size of R is less than what you divided by. This allows a Euclidean algorithm for finding things like GCD, right? So you can divide something by something and get a remainder smaller, right? That's essentially it. And Euclidean domains are very strong. They're stronger than principal ideal domains. So every ideal is general, and it's stronger than UFE. So one of the big theorems we had toward the end is any Euclidean domain is a principal ideal domain. And any principal ideal domain has unique factorization. That's the fundamental theorem of arithmetic. So every non-zero and non-unit element can be factored uniquely into prime elements. But yes,
Number 4 in the last chapter is of the integral domain.
okay. Let's look at this. Oh, consider the integral domain C from the square root of -6. Is that what you mean? Yeah. So these are just all complex numbers. Well, A plus B comes to square root of -6, but A, B are any integers. Same here, except with a radical -6. So I'm gonna need some stuff from previous problems here. We have this function called norm. This turns out to be A squared. There's also, I'm gonna use the same terminal here. these are actually two different functions. This one's defined as first. Your input is one of these crazy complex numbers. Notice your output is an integer. And there were some properties that I think we're gonna need that I will tell you what they're all about. Previous, it turns out for both of these, you have norm of alpha beta. So instead of writing out a plus b radical -6, c plus d radical -6, and all that alpha beta, it's multiplicative. Norm of alpha equal to 0, if and only if alpha is 0. And I mean complex number 0. And C for 3, norm of some element is equal to plus or minus 1, and only if alpha is even in its respect. And by the way, here's something even more convenient. No way are these ever going to be negative. These particular ones. Right? You're adding two positive numbers. There's no way it's okay. So this last one might be norm as 1. So here are the range, here are the norms. We're going to need this. Show that there's no element in C radical 6 going plus or minus 2 or plus or minus 3. By the way, no way it's ever going to be negative either. It's from the same argument. But this means that a squared plus 6b squared is equal to 2 or 3. Now, let me point out that if b is not 0, then this thing is at least 6. Right? So to be either 2 or 3, b must be 0. Is 2 or 3 a square? No. Okay, so that's it. That's the solution. Nothing about norm plus or minus 2 plus or minus. Right, okay. Show that c square root minus 6 is not equal to 8. Anybody see a bad factorization? Right? Something that's not unique. Check this out. I can factor -6 this way and this way. Actually, there's infinitely many examples. However, stuff I need to really show you that these are different factorizations, right? And I need to show you that these elements are irreducible. Clay. 2, 3, and minus right up to 6 are irreducible. I call these 3 elements. Let me prove this. First, norm. What's yes?
And the reason why we're not doing it to 0.
It doesn't make any difference because -1 is the unit, right? Because it's a verb. So whether I say minus or plus, it doesn't But yeah, you can put a -2 there, it's all good. What is the norm of 2? 4. It is 4, right? Because that's 2 plus 0 radical. See, this is 4. Okay. Let's suppose that I can break 2 down further into some exotic thing. This means that the norm of 2 is the norm of alpha beta, which is the norm of alpha, norm of beta. Right? Using my property, so 4 here is reducible. The norm of alpha and norm of beta can't be 1. Why is this? Because if the norm of alpha were 1, that would mean that alpha is a unit, right? And that doesn't count. If I'm assuming it's reducible, I'm assuming that I can break it down into 2 factors that are not units, right? So what are your choices? Well, remember, these norms are all integers. How can I factor 4? Well, I could have the norm of alpha 1 and the norm of beta 4, but that didn't work because I'm not level 1. I could have the norm of alpha be 4 and the norm of beta equal 1. That didn't work either. What's my only other choice? So it must be the case norm alpha, norm beta are both 2. Right? That's contradiction. Because in part A, it showed that there are no elements of there's nothing of norm 2. Right? These other arguments are very similar, and I'll go through that a little bit faster. If 3 equals alpha beta, then 9 equals norm alpha, norm beta. Right? This is very similar. Instead of squaring 2, I squared 3, right? And I've got the same problem. How can norm alpha, norm beta, what can norm alpha and norm beta be? Well, neither one of them can be 1 again, because that would mean that it's not reducible. So we also showed there are no elements in 3. So, okay. So 2 is irreducible, 3 is irreducible. What about radical -6? Well, now I have the norm of radical -6 is 6, isn't it? Well, 6 is a little bit more exotic. I've got a little bit more variety of what I can do. But again, we can assume norm alpha and norm beta not equal to 1. Because if either norm alpha or norm beta was 1, that would mean that it's a unit and I really haven't reduced anything, right? So what can I conclude? Well, if it reduces, then I have to have norm alpha is 2 and norm beta is 3, or the reverse, all right? By the way, let me point out that in this range, the only units are plus or minus one. Agreed? Those are the only units. And so we do indeed have a non-unique factorization. Irreducible, and they don't vary by a unit. Because the only units are plus or minus one, and it's clear, isn't it, that two is not plus or minus square root negative six. Everybody okay with that? In the last part, I said find an element with two irreducible factorizations of different weights in z square root negative 30. So with two irreducible factorizations. Weights. Yeah. Notice I have non-unique factorization here, but the least irreducible is same 1, 2. We're actually going to find some two points here. And let me spoil the surprise for you. And this is very similar to the last problem. I'll go through the details of one, but I think it's the same. Now, what do? We group 2 through 5, right? And make 30 for all of those, which they are. So now, notice that the left side of that has two irreducible factors. Radical negative 30 times radical negative 30, and the other side has. By the way, it's interesting, I did have to leave this ring to do that one because it turns out that this doesn't have unique factorization, and there are infinitely many examples. But every time you have a non-unique factorization, it's always in the same one. And this one is not. Yes.
So about UFDs, I'm kind of confused about how to show if it is or is not a UFD. So like, is that a UFD? No, because the n is not equal to n.
That's right. That's wrong. A UFD means that every element that's not zero and not a unit factors in only one way into irreducibles, or in fact primes. Right? This one doesn't even have the same length, but this one has. Oh, here's another way. If you have an atomic domain, so that is, when you have an integral domain where everything that's not zero and not a unit factors into irreducibles. If it's also the case, it's a UFD in that case, if and only if every irreducible is prime. If you look at this factorization right here, 2 is not prime because 2 divides, there's a product here, but it doesn't divide on one and the same. Okay? So because you have an irreducible that's not prime, it can't ever be good.
Could you do like a quick example of something that is a UFD?
See, for example, I'll give you a bunch. Any field, fields are stupid because everything is either zero or a unit. So it's vacuously a UFD because there's no non-zero, non-unit factor in the first place, right? But let's not be too silly. CX. In fact, that's one of the last theorems that I gave you all. any polynomial ring over UFD is UFD. So any number of variables, so Z and 6 variables is UFD. A field and some number of polynomial variables. Gaussian integers. Z going with square root -2. Z going with square root +2. Z joined with 1 plus the square root of -19/2. They're all of this. Actually, though, C is a UFD, and the easiest way to prove that is it's a PID, and then use that theorem I gave you to show that any of these are. Some of these, this one's also a Euclidean domain, so you can use that to show it's a UFD. This one's actually a PID. Some of these, as the number gets bigger, it's harder. And so awesome. If you have, you know how I had the negatives under the radical here? Well, it's known for these types of rings, there's only finite many UFDs, or adjoining the square root of a negative integer. There's only finite many. When you join the square root of a positive integer, nobody knows. I think the conventional wisdom is infinitely many are UFDs, but figure that one out, fortune and glory. So nobody knows. Okay, yes.
Einstein theorem criteria.
What's that now?
Is Einstein theorem disability criteria? Yeah.
I don't know yet. Right? I mean, it's fair game, but I'm not done with the exam. It's also bad to implement that, I think, right? Because all you need, you just need to remember, you know, you have this criteria. There's a prime that doesn't divide the leading term, but it divides all the others, and the square of that doesn't divide the constant term. Then the polynomial can only have constant factors. Okay, other questions? Yes.
For the first isomorphism here, does G have to be a finite group?
Yeah. Yeah. Being
So for number 3 on the fall 2025 exam, when it says that show that the kernel of phi is normal in G, could you just say by the first isomorphism theorem?
Oh, I see. If you're in a hurry, yes, come back and fix that up,
Okay.
right? Because I think I specifically did ask a question, right? The kernel is becoming more.
How would we show it otherwise?
What, that the kernel is normal?
Yeah, like I know that
You've
it's
got
also-
two things to do. You got to show actually that it's so. And you got to show it's normal as well. Okay, first of all, this is not the empty set. Can you name something that's in the kernels of any homomorphism?
yeah, density.
There you go. So it's not empty. So all we have to do is use the circular criteria. Right? So suppose X and Y are in the kernel of phi, then phi of X equals phi of Y is that into the H. Therefore, phi Y inverse, the inverse is also equal to that in H. Because the inverse, yeah. So if you look at phi of x, y inverse, this is phi x, phi y inverse, equals the identity, comes to identity, which is the identity. So, per phi is a subgroup. That's the subgroup criteria. So I showed that if I've got a random pair of elements, they're x and y, then x, y inverse is so.
Can you repeat really quickly about why phi of x equal phi of y?
Oh, because I'm assuming they're in the kernel.
Okay, yeah.
Well, so they're both the identity. Okay, so far? So that gets me that if I've got a subgroup, right? Now, the normality. I need to show that if x is in the kernel of phi, then any conjugate of x is also in the kernel. So let's just test that. This is phi of g inverse, phi of x, phi of g. Well, by assumption, phi of x is the identity because it's in the kernel, and that makes this collapse. And this is phi of g inverse g, which is phi of the identity of g, which is identity of h. And so, kernel phi is in fact normal. Yeah, I mean, it's, don't let proofs intimidate you. Often it helps just to write down some stuff right? This is what it means. This is where I'm going, right? This is what I need to show. I want to show something more. So, oftentimes with some problems, it kind of leads you to the solution. Okay, other questions?
Number 2 from 2025 assignments here. Elementary division of grade 5 here.
Oh, right. So what we're gonna. Some ladies, United States, 8. Okay, first thing you're gonna do is break these up into prime powers. This is 2 4 times 5. $96, I guess, is 32 times 3. Uh, 16 times 3. 8 times 7. R&D is, I guess, 2 times 9 is 5. Okay. Everybody with me up to this juncture. This is technically already in elementary algebra. But let's clean it up a little bit so that everybody knows, we all know what we're doing here. I'm gonna arrange this. Elementary advisor. I'm gonna arrange this by prize. Because that's working too. Let's see. Lord have mercy. Let's see. We got a 32 to 16. Make 2, I guess. So this next column I've got is 3. So what I got? 3, 3, and 9. Right, so it's the next one on the plate. It's 5. Got a 5. Another 5. And I guess I'm gonna go one left. 7. Okay, so notice that I've sort of arranged this. This is like the CLO Q sub assuming balance 2, C bar C is CLO 5 sub CLO 7. Everybody okay with that? Now, that's the element advisor and variant factor. I don't care. More folks out. No, so let's be bringing your pick these out to the 5th. Root squared 5. So I'm gonna do it. Everybody see how I got that? Combining the words. Pieces. And then 16 times 3 to 5 is 40. What wrong? Yes. First. And the next one is 16 times 3, so it's 48. And all that I've got left after this, I've taken everything out, it just keeps trailing. So it's just the 8. And by the way, the number of invariant factors you get here, you get 2, 8, 40, 240, and this huge number here. This divides this divides this divides this, and this divides this. And the number of them should be the longest piece that you have. This piece on 5, 3, 2, and 1, so it should be 5 invariant factors by itself. Yes,
That would have-
I'm sorry.
On the exam, do you have to write more than that, or is it just like that?
No, just, well, you might write out elementary advisor or something, so you don't need medication or something, but, yeah, I'm just, that's just fine. Just do a roadmap, there's no real proof to this, it's just, knowing how it's operating. Okay, others. Other questions? Yes.
On number 2 of spring 2019, of showing that the kernel of P is an ideal of all, is that essentially the same process as showing that it's a normal group?
Well, you don't have to show it's ideal there, so I would use like the ideal criteria. Um, So. Yeah, so to show it's an ideal. What did I say? Homomorphism. Okay, I didn't say it's commutative, so let's be careful here. So I kind of, I guess conspicuously didn't say anything about it being commutative. So let's make sure that we're careful here. Curve 50. Okay, so I'm gonna show as an ideal. So here, first thing I gotta do is show it's a subgroup, right? If you were in a hurry here, you could say something like, okay, this thing is first and foremost a homomorphic groups and the kernel is a subgroup. We already know this, right? But if you got time, I'll come up with it. I'm gonna do something still careful here. So notice the zeros in the kernel phi, so kernel phi is not empty. So I'm gonna show it's a subgroup. Right? So I'm gonna show first. So let's let X, Y, kernel phi. So this means phi of X, 0, S phi of Y. So if we look at phi of X minus Y, this is phi of X minus phi of Y. Zero minus one is zero. Therefore, curl of the R is silver. Now, we have to show it sus. It's an ideal, it's a vacuum point. We gotta show it such from both sides. I didn't say. So let's let X. So that's zero. And then R. Well, if you look at P or X, it's P of R, P of X, just P of R, and zero, which is zero, and P of XR, is P of X, P of R, which is zero plus P of R, which is zero. So, it's a subgroup and such stuff in both sides. Okay, any questions on that? Okay, other questions? On what you say?
That example.
Same.
Uses.
Write the class equation. Explain the notation used and use it to show why finding P of second month's triple seven. Okay. The class equation says G is fine. The order of G is the order of 17 plus G 7 X G. Well, it's about C G such CX such Z. Well, that's G. Centralized from G of XI is 17 G. So it's GXI is XIG. So this is all the stuff used with XI. And I got to tell you what the XI's are. X1, X2, up to XN are representatives of non-central consciousness. So basically, these are what you take and say everything that's not the center, pick something out of one of the orbits of those elements. Now, suppose so it's fine. We'll say that the order of G equal P to the n power. Let me point out that since xi is not in the center. Right. So each of these xi's are not the center. Then central alpha g of xi is a proper subgroup. That is that
why does xi not being in the center imply that this is a proper subgroup?
well, because what happens if it is in the center, then the centralized with this is all G, right? Because what if it's in the center, everything in G comes with it, right? Since it's not centered, there has to be at least something in there that doesn't communicate, right? So that's why it has to be proper. And I'll make the further observation that this is a subgroup of G. So this is also a P group. So it has to have order P to the K power. And since it's proper, that K must be strictly less than N. Therefore, each one of these things, which is the order of G, of the order of G, that's which is P A, is equal to P and M minus K, which is finger boundary. Right? So the upshot here is this. So P divides 1, 2, 6, 3, P. And P divides this funny little function there. So P divides this thing, and P divides every one of these. So P divides this thing. So this has got a factor of P. This whole thing is a factor of P. This has so this has P. Ready? The order of the center has to be at least 1, because if nothing else, the identity is in the center. Right? Therefore, it must be very better than 8, because it's divisible by P. It can't be 0 because it's got at least 1 element. So if it's divisible by P, it's got to have at least P elements in it. And so that's the conclusion we come to, that the center, it's got a non-trivial center, because the center of the P group has to have at least P elements in it. Does that make sense? Okay, other questions?
Did you do number 5 of the same year?
Oh, is this counting all the units?
Yeah.
And whatnot? Okay, yeah. Count the units and the 0 files and C8 plus C. think actually it's easier for me to, you can do this directly if you so desire. But I'm gonna do this, I'm gonna do this prime now. These are separate. So remember the Euler feed function. This counts the number of units. Okay. And since I've separated this out, the P to K parts. So the number of units are the number of units. So what we have first, C8. So this should be 4 times 1, so number of units. Ready? Just using that. In fact, basically, C8 is 0, 1, 2, 3, 4, 5, 6, 7, right? All the odd things are units because they're relatively prime too, and all the even things are 0. C4. Similarly, you've got 2 here. Z5, that's convenient because it's prime, it's 4. 5 to the 0 times 5 minus 4. So be a unit in this thing, you have to be a unit in all 3 quarters, right? So if I'm going to count, I've got 4 choices from the unit here, 2 here, 4 here. So I guess that comes to 32. Looks like there's 32 units. How many zeros?
Would it be everything else in this case?
It's a finite range, so it'll be everything else. And in this case, the number of elements in C8, C4, C5 is 160. Yes. So number of 0 divisors, 30 cell, 160 minus 32.
You said you can, it's everything else if if the rings are finite.
If the ring is finite and everything is either a unit or a 0 divisor. Okay. I'll be my office all day tomorrow, except I've got to step out for my 10 to maybe dinner for that exam, but I'll be here till it's 3 weeks.
And you said you'll be there starting at like
7.
7?
Yeah,
Okay.
yeah.